with this summer school is that we keep talking about the same things for pretty much a whole week, right? And one of the benefits of that is that you get to see a lot of different views of the same thing. So I'm also going to try and start off a little bit with giving a bit of motivation of why I work on these things and why I think that's useful. And then I'm also going to give, as I think you've probably seen about 4 or 5 already, introductions to Gaussian processes, and I'm going to give a brief and slightly different one, I hope, before we come into the meat of the material, which is going to be about how you can deal with GPs in an unsupervised setting. And then I'm also going to talk about composite Gaussian processes, which I clearly can't spell, but hopefully I will still be able to make some sense of them when I talk about them. So the first thing that I wanted to basically start off with is start as far away as possible of just thinking about what we're actually doing. So let's talk about statistical learning theory and think about what we're actually doing when we are doing machine learning. So these are the premises. So we have a space of functions, or in the most general setting, it's a space of hypotheses, which are possible solutions. Then we have some form of learning algorithm, A. And what this learning algorithm does is that it somehow traverses or searches through this space of hypotheses. Then we have a set of training data, S. So we can think of these as inputs and outputs, X and Y if we want to. And they come from some distribution of the data, P. And now we have some form of loss function. So we have a loss function that we can evaluate, given that we have taken our search algorithm, applied it to this space of hypothesis, and use this data S. We get out one possible solution, and we can evaluate that over any set of data. And the idea is that this loss function should somehow encode some benefits or some preference of what we deem to be good. So now, how do we actually approach machine learning if we take these components? Well, the most sensible way would be to pick the solution that minimizes the expected loss. So what you would now do is you would simply take the integral, or the expectation over the data, over this loss. So that's effectively, and why this makes sense, right, is that now you basically say you want to have the smallest possible loss on average, right, where you take in the contribution of how common the data is. Well, the trick with this, and why you can never ever do this, is that we don't have the distribution of the data. We don't have P. If we have P, well, we don't need to do any of these things, right? So what we effectively always do is that we take the empirical loss instead. So what we do is that we say, I have some training data, and now I evaluate my loss on this training data. And I pick now the solution AFS that somehow minimize this empirical loss. Well, the tricky thing with this, and this is what then is called the no free lunch theorem, right, is that we can come up with a combination of data, algorithm, and hypothesis space that gives this error a completely arbitrary value. So one way of thinking about this is that we just take an example, right? So now I'm supposed to find some form of function in this space. So if I give a data point here, how many possible functions goes through this data point? Well, infinitely. I can keep adding data like this, and I still have infinitely possible solutions that gives exactly the same error on this data. So what we need to do is that we need to add something else to this, right? And now we have these 3 components, which we talked about before. We got our algorithm, I got my hypothesis space, or I have my data. And to each of them, I need to add, or I can add some form of regularization so that I find a solution that somehow makes sense, right? So the first thing is you can think about adding some form of structure to how you search for the solution. So this would be a bit like thinking, well, actually, in this energy landscape that I have, the solution that lies to the left of me, oh, I don't really like that because it does something that I don't want. So I'm going to put a patch over my left eye and I don't see anything. Then I see that, oh, there's these very, very narrow, small local minimas. I don't want them either. So I'm going to put very, very big shoes on so that I don't fall into them. And you can kind of see that I'm kind of making fun of this. And if you like Monty Python, I kind of see trying to put constraints on my optimization problem a little bit like trying to do the Ministry of Silly Walks. The other thing you can think of is that you can somehow decide and curate your data so that you learn only specific certain things that you're interested in. So you can take this example where I have my data, which is distributed actually according to the blue density. But now I decide to actually, the thing that I really want to learn is the stuff that's up there in the red. So I can pick only that data, or what's even more common is that you do what's called data augmentation. So for example, you want one solution that's invariant to something. So for example, in images, I want them to be invariant to rotation. So now I augment my data set with all possible rotations of an image. Now I hope my solution will pick that. This is really, really hard to do. And of course, as more data I add, the more expensive inference is going to be. So the last thing that you would put something on or think is to actually try and put structure on my hypothesis space directly. So I actually say, can I give a preference towards all possible solutions so that I can weigh the solutions, not just how well they fit the data, but actually what I have for preference for them before. And that will be placing structure over the hypothesis space. So actually the possible functions that I can learn. And clearly, this is really what this summer school is about, because what we're mainly talking about, how can we place structure over the space of functions using this thing called Gaussian processes. So just to highlight this, because I think there's a narrative at the moment where we sometimes it's easy to believe that somehow machine learning have circumvented this no free lunch. And there seems to be a narrative at the moment where the more flexible a model is, the better it is. And flexible in my group, we call it the F word, and it's something that you shouldn't say because it's a very strange way to argue about the model. What I would say instead is that basically the best possible model that you can have is something that has infinite support, so that might possibly be flexible, so that it's something that doesn't exclude any possible solution, but it's something that you can parameterize in such a way so that it puts a very, very strong preference over certain solutions. So I call that something that has a very, very focused mass. And what I hope you should think about when you think about Gaussian processes later on is that this is something that has exactly this characteristic. It's something that doesn't exclude any solution, but it places its probability mass in a very, very, very narrow region of space. But you can move this region around. And then the last thing, which really comes to the bottom of this, what this summer school is about, is that the other thing that the no free lunch says is that you can only ever interpret your solution in the light of the assumptions that you've made, right? You can take this just as a seeing that if the no free lunch tells me that there's no way I can find infinitely possible solutions that have the same error. If I now give you one solution, this has only been selected based on my prior assumptions. That means that that hypothesis that I finally come up with can only ever be interpreted in light of the assumptions that I've made. So a funny way of saying this is that even Boris Johnson can sometimes say something clever, but you have to go back and look at his assumptions, and he's a despicable human being, which means everything he says is still false. Good. So that is actually what the summer school is actually called. So if you've seen, if you would have been in Sheffield, you would have gotten notebooks, and on this notebooks there's something Latin written, and what it basically says is that the posterior is the student of the prior, which effectively means that you can only ever interpret your solution in light of the assumptions that you made. Good. So that was basically my first motivation to why I want to work on Gaussian processes, because they have exactly these characteristics. They allow me to place structure on the space of hypothesis that I'm interested in, and they have the characteristic that they don't exclude anything, but at the same time, I can, by parameterizing them in the correct way, really narrow in and put very strong prior assumptions. So I can focus and concentrate their probability mass. So now I'm going to give my engineering-y but explanation of what I think a Gaussian process is, how we come up with this. So basically, we're back to this graph where we started off. So I have this space of possible functions, or I have this space where I want to draw functions over. Now I want to add structure to this plane. How can I add structure? Well, the first thing that we do when we think about Gaussian processes is that let's take a line. Let's take a slice of this space. So I slice this from -infinity to +infinity at this specific x value. What I know about the function is that the function will cut this line and once and only once. So in a Gaussian process, what we do is that we specify a belief in where we think the function will cut this line. And we say that that's a Gaussian. So now you can argue if that's right or wrong. It definitely has certain limitations, but the benefit that it has is that this Gaussian have probability mass everywhere, which means I haven't excluded any possible intersection between this line and the function. I allow them all, but I can focus most of the probability mass in a very small region if I want. Now, there's nothing special about x equal to 3, so I can make the same argument for x equal to 2, or -2 in this case, I think it is. And now I just have these two Gaussian slices. And actually, if I made it at these 2 points, I can say that that's true anywhere. And now, because the question is then, how many slices can I take along the real line? Well, I can take infinitely many. So that leads me to this Gaussian tube, this infinite set of marginals, which we call a Gaussian process. So it's not really interesting to just think about the function in terms of where it intersects at a specific slice. The characteristics of the function really comes from, say that I know the value at the green slice. What does the green slice tell me about the value at the red slice? That's really how I think about the characteristics of the function. So let's now say that I know that at -2, the value, the y value, is actually 2. We'll say that I know it with a little bit of noise. So I have this tiny Gaussian. I'm very certain that actually the intersection at -2 is very close to 2. Now, the way I parameterize a Gaussian process is that I think what does knowing the value at -2 tell me about the slice at 3? Well, either it can tell me nothing, so I'm basically back to the assumption that I had before I knew the green one, so basically my prior assumption, or it tells me everything, and I just translate. If I know it's -2, it's pretty much I know exactly the same information at 3, or quite possibly it's somewhere in between these. And now specifying this, how the information flows from between these two slices, is exactly what a Gaussian process does, right? So you think about looking at these two slices jointly. So here I have 3 Gaussian distributions, 2D, and at the x-axis I have the value at the green slice. Now, if I parameterize the covariance element up here, it tells me exactly how much information flows between the x and the y. So if I know that the value in this joint Gaussian, if the value at the green slice is 1, it gives me this marginal distribution over the red line. And of course, now if I just increase the covariance, now the information, if I know it's 1, becomes much more centered around what the value should be at the green slice. So basically, this is then the nice thing. Now I can specify not the 2-dimensional joint, but I can specify in this case, I think a 300-dimensional joint Gaussian distribution. And I just draw a sample from that and I can generate this. And you saw this yesterday. And what's even more cool is that given that I now have some data, actually the posterior distribution, so knowing exactly the samples that agrees with the data that I've seen, is something that you can derive in closed form. And this is really, really cool, right? Taking all these samples here and just picking out the ones that goes through the point on the right is something that I can do in closed form. And that's super exciting. So just a slight recommendation, if you want to see actually how these things work and just getting how really simple they are, one thing that I would definitely recommend for you is to derive all the Gaussian identities for yourself. If you take the joint, deriving the marginal and the conditional distribution is something that's really worthwhile having done at least once, even though we nearly always just take it for truth. But it's a nice exercise to do, and I think it's something, if you want to work in GPs, it's worthwhile doing it once, because I think it really tells you a lot of things. So now I'm going to take a slightly more theoretical view on just what we said. So we keep talking about this infinite dimensional object called the Gaussian process, but then as soon as we work with them, we're only working with these Gaussian distributions. And I just wanted to make the connection between these clear, because it's something that's going to come up a bit later on when we talk about unsupervised methods and when we talk about how we do inference in them. So the question you can ask yourself is that, well, if there is a Gaussian distribution and a Gaussian process, does all distributions have an infinite generalization in terms of a process? So there is this thing called Kolmogorov's existence or extension theorem, which states the two things that we need to hold for a finite dimensional probability measure to be an actual realization of an underlying infinite object called the stochastic process. So we'll just take these and look at what they mean. So the first property is the exchangeable property. So what we have is that we have a set of permutations, all possible permutations pi. We have a set of measurable sets f, and we have a probability measure nu. So the exchangeable property means that if I permute the measure and if I permute the sets, that has no, in the same way, that has no, it doesn't make any difference. What the marginal property means is that if I extend the possible sets with something, and then I take the measure at only a subset of that, the subset doesn't change. So this might be a bit tricky to see, but both of these things are trivially true for a Gaussian. So let's look first at the exchangeable property. So if I have this two-dimensional Gaussian, one of the very cool things which you see when you prove the Gaussian identities, if I now take this thing here, and now I am going to flip x1 and x2. So I flip x2 and x1. Now the only thing I need to do is actually flip the elements in the mean and the covariance. Nothing else happens. So another graphically to see this, if I take this two-dimensional Gaussian, x0, x1, as we had before, and now if I just flip the axes, it's the same. If I just have to flip the measure as well, and all evaluations of this are going to stay exactly the same. The marginal property is just saying that if I now take this two-dimensional Gaussian and I integrate out x2, the only thing I get is that I get mu1 and I pick out the mean and I pick out the covariance. If instead I would take a much, much bigger Gaussian, a massive Gaussian, and now I do the same thing, I integrate out everything else, actually this part here stays exactly the same. And this is really what we do when we do a Gaussian process, because actually what you need to now think of is this n going towards infinity. There's infinitely many possible slices along this line, and I've just decided to pick a finite number of them. But that doesn't change the process. So another way of you seeing this graphically is that if I take x0 here, now if I take the marginal of this coming from the distribution where x1 looks like this and the joint looks like this stays the same. Now if I alter the marginal of the other one and the covariance element, the x0 still looks the same. The marginal distribution of this still looks the same. So one way then of seeing, which I like to think about what a Gaussian process actually is and the relationship, is that the Gaussian process is this infinite dimensional thing, which we can't write down, which we can't deal with. And then you just have a projection matrix, which is axis aligned, which just picks out a set of marginals from this, boom, projects this down, and I get my Gaussian distribution. And this is basically the way to think, or I like to think about Gaussian processes, because I, for a long time, found it quite confusing about thinking about this. We talk about this infinite object, but we never deal with it. And we are going to exploit these facts when we do approximate inference a little bit later on. Okay, so that was my slightly longer than intended introduction to GPs and my motivation for why I like working with GPs. Now we're going to come more into the meat of things when we're going to talk about how we can deal with unsupervised learning in the setting of Gaussian processes and why they are really, really useful for this task. So far, we've looked at regression problems a lot. So regression problems is where I'm interested in finding this conditional distribution P of y given x. So I've been given data y, where each y value have a corresponding x. So now I'm effectively trying to find the distribution over y, which is indexed by x, so that at any point when I do prediction, I can just say, I plug in an x, and x completely defines the distribution over y. Now, the unsupervised setting that we are going to look at now is that I have y, but I don't have any corresponding x's. What I want to find is that I want to find sensible x's that somehow indices y. So graphically, the way I like to think about this is thinking about it like an abacus. So say if, when we were doing regression before, we had x and y values scattered along this plane, and then we wanted to find a function that binds them together. Now the setting is different. We don't have any x values. I'm free to choose them. So think about these stars as basically balls on an abacus where you can pull them along and give them an x value. Our task is now to pull them out so that each one of them gets an x value. Okay, well, that should be fairly easy, right? I can do this. That's definitely giving each y value an x value. I can do this. That's another solution. I can do this if I want. I can do tons of different things, right? All of these are, again, coming back to the no free lunch theorem. Well, all of these are solutions, right? So what we need to now do is add something that tells me a preference over these solutions, that says there's one of these that I prefer more than others. And we're going to use Gaussian processes for this. So if we go a bit further on, what I'm now going to do is that I'm going to just give some random x positions to each y value, and then I'm going to fit a Gaussian process to it according to some prior, and then I'm going to evaluate how much the GP likes those x values effectively. So here is one. Now my prior is over very, very smooth functions. I think this is a squared exponential covariance. And you can see, sure, there is definitely functions that goes through these points, but it had to wiggle quite a bit in order to fit this. The value that you can see at the bottom here is actually the value that I'm trying, it's the likely, I think there's a minus missing, but I'm trying to find it should be the negative log likelihood, I think. So at least I'm trying to, my rating of each of these x configurations should be, that value should be as low as possible. So I have this one. I can also put the x values in this. Now you can see this value became much lower because this here fits my prior assumption. And my prior assumption was on smooth functions. This fits my prior much better. This here is actually equal. This also fits my prior really well. And this one here is slightly worse. So a GP can actually, in this setting, provide me with a preference over which functions that I like, and therefore implicitly give me the x location. So that's super nice, right? That's really easy. So we can use GPs for unsupervised learning. But there's a trick to this. There's something that we're missing. So say that I have specified in this case a prior, I have a preference that says the smoother the function is, the more I like it, right? Well, if I have no constraints on x, there's a very easy way to make a function basically pretty flat. And that is just push these x values as far as humanly possible away from each other. Now I can fit them with pretty much a line with nearly no slope, right? So there's a trade-off here which we need to take into account. We both need to place a preference over that the x values in the configuration the x value should have, and also what the function should be. So,
Carl, can I ask a quick question?
Shoot.
Right, or pass one on. If both x and y are one-dimensional,
yeah.
which I guess they are, yeah, would there be a unique x recovered with a particular GP prior by maximizing the log likelihood?
Would there be a unique x?
Yeah.
Well, there will be, if I maximize the log likelihood, there will be a unique x, absolutely. There won't be a unique f, because there's still infinitely many possible functions that goes through any configuration of x, but I will have my GP prior will still have a peak in it because it's still a Gaussian process. So we'd have a mean prediction, which is the most probable one that goes through this.
I see. Yeah, that makes sense.
Yeah. So the deal here is I kind of like to, what we need to do in order, hopefully this makes sense, right? I'm not sure if people can see my hands. I'm waving my hands a lot generally when I talk. But basically, you can think about if you want to have a flat function, if you now think about, if I used scale the x-axis here, in this case, and make it 10 times longer, I just increase the distance by 10 between every x. The GP is going to like that. It's just going to be, oh, nice, this is much smoother. Well, why not make it 100 times longer? Oh, I like that even more. So what we really want to do, and the easiest way to do, think about, let's say we put the Gaussian prior over x, and you say, you know what, I don't want you to go out very, very far away. So let's think about that for a bit. What we then need to do is that when we're looking at this P of y, we can't just say, do the regression example, which was what I actually did just before, is that I say, you know what, I'm just going to type a GP prior, and then I'm just going to maximize x for it and do a maximum likelihood. What I actually need to do is I need to place a prior over x and also integrate that out, where P of f describes my assumption or my notion of complexity, if you want, in the functions that I prefer, and P of x expresses our belief or assumptions in the structure of the latent space. So now if you say this, great. Now let's just do Bayesian inference, churn the handle, and we're all going to be happy, right? And I can finish my talk after 35 minutes. But there's going to be a twist to that. So let's just think about this. The GP prior, P of f given x, looks something like this. It's a Gaussian, so it's an exponential. Inside the exponential sits the covariance element in an inverse. The x's are inside this K matrix. And if I use something like a squared exponential kernel, each element in this K is an exponential, and that's where the x is. Then I have a likelihood, and the likelihood itself is also an exponential, and that's where f comes in. So now let's say I now specify a prior over x, which is also an exponential. Let's just now think about the relationship between x and y. Well, it's ridiculously complicated, right? First, x sits somewhere in an exponential, which sits in an exponential, which sits in an inverse inside an exponential, which should go through an exponential. You can't solve this. It's impossible. This is as intractable as it gets. So this integral here is not feasible. The other way of saying this, more hand-wavy possibly, is that the relationship between x and y is non-linear through f. And you need to push this Gaussian distribution through a general function. You have no idea what distribution comes out on the other side, and it's not certain that you can parameterize this, which means this integral is not analytically tractable in the general case, which means we need to do approximations. And now this is what we're going to talk about. And I have this nice quote. I think Neil is going to talk tomorrow. He usually talks before me, and he's going to talk about Laplace, I'm sure. And Laplace has a saying, which is that nature laughs at the difficulties of integration. And that is definitely true.
Cool.
So
before we go into that, can I just ask one question? I think there's some confusion maybe, or some clarity. So I think everyone's got the hang of the idea of priors on the length scales and stuff from the last few lectures and things. I think that's kind of like everyone's got a grip on that. But maybe they're confused about this idea of putting a prior on X. So I'll just ask the question. So what's the difference between putting a prior on X versus a prior on the length scale? Does that help with identifiability? So I guess that's kind of...
Yes, it does. So you can think about it in this way. So there's an interesting interaction between the length scale and the prior over X. So for example, if I place a prior over the length scale, so that I say I want a function that varies over this. I'm drawing it in the air again, but that varies over a certain range. Now, if I don't have a prior over X, I can just move X to exactly fit that length scale, right? That's super easy because I have no preference over what X is. Now, if I place and now what we generally do in the GP prior in unsupervised learning is that we say, I prefer the smoothest possible function. So you basically want the length scale to be as long as possible. Well, great. I will now just put the X's as far away as possible so that they exactly fit the length scale that you wanted.
Right.
So therefore you get this, there is this interaction between them, and you need to tie both ends down. So that's why basically I had this image of this seesaw thing here. It's like if you only have one end of this, it's like one of these people is basically the GP prior or the prior over the length scale. Well, if you don't know what the X's is, you can do whatever you want, right? I can always find the X's that gives you exactly what you want.
Yeah, I see. Yeah. Okay. So there's a okay. I see now. Yeah. I think that's hopefully
therefore
the
you need to
question.
balance the two together.
Yeah, that makes sense. Yeah, hopefully that answers the question. If people still need to answer questions, don't forget you can ask at the roundtable discussion later.
Yeah, and please do. This is really good. This is really good to stop in out there. It's also a new world for me giving non-physical or virtual lectures. So I
think it's for everybody. The lack of whiteboard is frustrating, though. I get
the lack of whiteboard is frustrating. So
cool. Yep. Go ahead.
What we're going to do now is that if you buy this concept, that basically I need, in order to basically circumvent the no free lunch, or basically I need to tie down both ends. I both need to tie down the GP end, which you've talked sufficiently about, and I also need to tie down the latent structure, the actual X's end. Now, you buy that is not tractable. Now we need to do approximate inference. So I'm now going to do what we normally do in GPs, is that we do variational inference on these. And I'm sure that some of you have seen variational inference. I'm going to give a brief introduction to it, which I think possibly is a little bit different than you will often see it. And then we are going to apply this to GPs. And what you're going to see is that it's not straightforward to apply this to GPs. We actually need to do a couple of tricks to get it to work. But for now, for the bit that we're going to talk just right now, you can forget about GPs. Just think about general probabilistic models. So what we have is that I have some data Y, and now I am going to parameterize up a statistical model that can generate Y. And what I want is that I want to integrate out everything I make assumptions over so that I get the object P of Y. Somehow P of Y is intractable. So the way we think about variational inference is this. So Mike can answer me. I'm going to use my mouse to draw things now. We'll see if people see this.
Yeah.
It's visible. Okay. Yeah. So basically, let's just assume that rather than having f's and x's and everything, I just have this integral here. So I have p of y given x, which is what I've specified. This is my generative model. I specify a prior p of x, and I now want to integrate out the belief over x so that I just get p of y. This integral is intractable. I can't solve it. This is annoying. So one way of looking at this graphically is that the leftmost model is what I've specified. The middle one is what I want, where I integrate out x, but I can't get it. Another way of writing p of y is to not write it as an integral, but just write base rule. And base rule in this case would be p of y given x, my model, times my prior, divided by p of x given y, so my posterior. This is equal to this. So now this is this term here. So now the top two terms here I've specified, so I know them. This is intractable. This is also intractable. But in order to, if I'm searching for p of y, base rule implies that it's equivalent to find the denominator here. If I know the posterior distribution, p of x given y, well, I just need to do base rule and I get this one. So actually, I can think of the problem of solving this integral as also the problem of finding this posterior distribution. And the way we're going to do this now, which this eventually will lead to, is that we're going to say that I'm going to formulate a distribution qx that has a set of parameters theta, where these parameters contains all the statistics that I need to describe the posterior distribution over x such that I don't need y. So effectively, I want to find q theta x so that it approximates p of x given y. If I can do that, well, effectively, I can now plug that in here and I can get this. If that would be equal, I would also get this, and therefore implicitly have solved this intractable integral. So we'll see if that makes sense. So now we're going to do, please stop me if this is now gets confusing, because we're going to do a rather long derivation to try and show how we can solve this. So this is the object that we're interested in, p of y. We are generally going to look at the log of p of y instead of p of y, because it's going to make everything much nicer to work with. So now what I'm going to do is that I want to connect p of y to the posterior, right? Because that's the thing that I wanted to find. That was what we said. I want to find this q, or something that approximates the posterior. So I'm just writing something that now looks completely nonsensical. I take log p of y, and then I just add this integral, which is nothing, it's log 1, and that's it, right? Now, I also want to connect this to some distribution q. So what I'm going to do, just to be able to merge these on the same integral, I'm going to add q of x dx, which again, this is a distribution, so it just integrates to 1. I've done nothing. And I'm adding the same thing here, right? I've done nothing. This is just log p of y. But now, because I've written them both as integrals over x, I can now merge these two integrals. So if I merge these two integrals, I get qx log, and up here I have the posterior distribution times p of y, and then I got the posterior distribution in the denominator. What I'm now going to do is that I'm going to say that P of X given Y times P of Y is just a joint, right? So skip the leftmost term. So what I do now is that I pick out the numerator and Q of X, and then I pick out the denominator, Q and the log 1 over the posterior, and then, because I want to distribute some Q of X's, I'm going to add this nonsensical term, Q of X, Q of X, Q of X. Now, what I'm going to do is that I'm going to move one of the Q of X's over into this integral over here, which leads me to these three terms. I got something Q of X log Q of X, 1 over Q of X. This here is probably something I can compute. I got an integral Q of X log P of X given Y. This here is the joint distribution. It's not the posterior. The joint distribution I get by just multiplying two terms that I know, P of Y given X times P of X. And then I got this term here. This term here is the term that contains the element that is intractable. All these terms here in the blue are most likely tractable, but this term here is not, P of X given Y. So now we can look at that term in specific. So we are going to use, let's actually go back to that one afterwards. So that term there is called the KL divergence, or the Kullback-Leibler divergence. So it's QX log QX over P of X given Y. Now, what we can do is that I'm just going to flip the numerator and denominator and pick out a minus sign from this. Now, what I can do, this is what the previous slides were, we're going to jump back. Now, if I move the log, because the log is a concave function, if I move the log outside this integral, now I get Q of X over Q of X, so those two cancel, and I get P of X given Y integrated over X, which is just 1. Minus log 1 is just 0. So now I know that this KL term there is always larger or equal than 0. Right? So that's the first thing I need to know. The other thing is I can check when it is 0, and this is quite easy. So if I assume that Q of X is equal to P of X given Y, and I just plug this in, now I get P of X given Y over P of X given Y, which means I get 0. So this term here, the KL divergence, is 0 when Q of X is equal to the posterior, when I am allowed to exactly cut that dependency between Y and X, and it's always positive. That's the two things that I know. So we can skip these terms. I'm just running out of time a little bit. So that means if I now write up exactly what we had before, I had those two terms that were in blue initially. They contain Q of X, this term here, which was just Q of X log 1 over Q of X. And then I got this second term, which was Q of X and the joint distribution. And then I had this term that was red, which is the thing that I probably can't compute, but that I know is always positive and is equal to 0 if Q of X is equal to P of X given Y. So what that means is that if I drop this thing, because I know it always contributes a positive thing to log P of Y, I know that the two remaining terms is a lower bound on log P of Y. And if I can compute these terms, I can find the Q of X, or rather find a theta, the parameterization of Q of X, such that I maximize this lower bound. Implicitly, I am then minimizing this. So graphically, another way of looking at it is this. We formulated log p of y in terms of an intractable term, this KL term, plus a hopefully tractable term, L. If I maximize this brown thing, I'm effectively implicitly minimizing this and therefore picking a Q that is equal to P, ideally. So, now,
can I
that's
just
the top.
There's one little question, which I guess has been answered. Okay, so I guess people have seen different ways of doing that derivation. So one of the questions was, why not start this derivation, like start it by minimizing the KL?
Yeah, so this is very good. So I like this question. So the reason why I don't do this is that I think it's, let me see, where was I? I think it's, yeah, this is the question. So this is the Jensen inequality of the log, right? So if the KL divergence is arbitrary, why would I pick the KL divergence? If you're looking for a measure to minimize, you can pick whatever measure that you want. The reason why the KL divergence pops up is because I decide to use the Jensen inequality with a log. This is why this bound comes up. This is effectively the bound. Now, I could choose another concave or convex function that will give me a different bound.
Right.
So actually, the choice is not the log, or the choice is not the KL divergence. The choice is what convex or concave function that you use that induces the bound.
Yeah.
Because there's nothing right or wrong with the KL. What we should argue about is the log a good thing. And now you can question, where are we? Are we here in the log?
Right.
Or are we up here in the log where it's quite nice and happy?
Yeah.
This really is the question.
Yeah, no, I didn't appreciate that. That was what drove it.
Yeah.
What was the? I've seen people use alternative tricks instead of using alternative things, and instead of the KL, often they swap the direction things. Do you want to comment on that?
Yeah,
too? Is that
exactly. You can swap the direction for the KL. You can also think about, there's a whole class of other types of divergence measures that just leads to different bounds. You're effectively just trying to come up with something that allows you a lower bound. And it was a really good question to get. And the reason why I do the derivation in this way is simply to hope for that question. And that's why I don't like when you start off by saying, we're going to minimize the KL divergence. Yeah. I don't know why I should minimize the KL divergence. And the justification for the KL divergence or not being right comes down to if the log is a good function to use or not.
Yeah, I see. Yeah. No, hopefully that answered the question. I think definitely. And that's actually given me some intuition on this that I didn't have before. Cool. Thanks. Hopefully everyone else is funny.
So the nice thing, obviously, like we can think about, why would I ever use the log? Well, I use the log because most of my distributions are exponentials, and the log of an exponential is generally nice and easy, right? You can come up with another function, but now you're not going to get rid of your exponential, and you're probably going to have a horrible, nasty integral to use. And that's why we generally use the log. So to motivate why this is possibly a sensible thing to do, I'm going to quote, say, 3 things that Ryan Adams said in the Talking Machines podcast when asked about why would you do variational inference. So the first thing he says is that what I'm asked to do is to compute the expectation over the joint distribution. The joint distribution you should have. If you don't have the joint distribution, if you can't formulate the joint distribution, well, your problem is not inference. Your problem is that you don't have a model. So that is something that you should be able to have. And the joint distribution you get by multiplication, not integration. And multiplication should be fairly straightforward to do. Second thing is, you're taking the expectation of a log if you do the KL. That is usually easier than taking the expectation because of what we said before. Most distributions that we work with are exponentials. And then the last thing is the expectation is over Q, and you're allowed to choose Q, which means you can pick a distribution so that you can compute this expectation. And that is his motivation, which I kind of agree a lot with. So now then, this is our final thing. So expectation Q, log joint distribution, and then this term here, which just involves Q, which should be fairly trivial to compute. So now we are going to put our Gaussian process hat back on. And now we're just going to try and compute this for a GP. And we are going to try and integrate out X. And so let's just do this. So what we have here is the joint distribution. So remember, we got P of Y given F, which is our likelihood. We got P of F given X, which is our prior over the GP. And then we got P of X, which is our prior over the latent space. Dunk. And then we got, in this case, we're just dealing with X. So we try to integrate out X. So we blow this up and write P of Y given F, P of F given X, P of X. Now I can take out P of X, Q of X from this, and I get this KL term between the approximate posterior over X and the prior over X. And then I got this term here, which should be integrated over X. So I'm going to call this term, because otherwise the math is going to be, it just takes too much space. I'm going to call this term here L tilde, and we're going to try and work with this one, and we're just going to add this term back on the last few slides. So now this is the thing. Oh, sorry, I've added a DF here as well. Now this is the thing that we need to integrate over. Is this now tractable? No, because I still have exactly the same problem as I had before. We're still trying to push X through F. So X here is non-linearly, it sits in this covariance matrix in the inverse inside the exponential in this, that then goes through here. We haven't actually done anything. So actually doing this for a GP just won't work. This integral here is still not tractable. So I can't do it. And that's the issue. Cool. So now...
Can I interrupt really quickly? Sorry, with a quick question, just because I think this is the thing I got stuck on when I first saw this, could you give some intuition what Q of X looks like? Yeah. Is it one distribution over all of X, or family, or...
Exactly. Yeah. So I've specifically avoided writing up what it could be. But let's say that one set, like the easiest possible way you could do Q of X, right, would be, for example, picking an independent Gaussian per X. So you say it's a big Gaussian blob, yeah, right? So now I'm just saying that my posterior is also this Gaussian blob, right? That would be one way of thinking about it. Or I would say that my posterior is a tiny Gaussian per latent variable. You could also.
Right, yeah.
Yeah. So, but you can see the key thing is to see that we haven't, nothing's gotten any better, right? Effectively, I still have this thing which I can't deal with. Like the integral actually looks exactly the same as in the previous case. In the previous case, I had a P of F here and not the log, right? And we needed to integrate that out. Now I just have a log of this, which is not going to help me massively. And I still have this non-linear relationship between X and Y. So I can't do this. So what we're going to do, and this is a really, really cute trick that was, if you want to read the literature, it was first, there's a PhD thesis by Joaquin Candero Candela from 2005. And then there is some really, really nice work by Michalis Tsitsias, 2008, I think the first paper is from. So what we're going to do is we're actually going to go back now and think about the way we introduce the Gaussian process as a stochastic process. These two things where we said the marginal property and is something that we're actually going to exploit. So what we're going to do, we're going to do something which from the beginning doesn't make any sense at all. So remember that we've specified the Gaussian process, right? The Gaussian process is infinite. Then we saw data at a specific finite y, right? Not the x's, but because there were finite y's, each one of them had a finite number of x's as well. Now I'm just going to say that, well, I can also look at another set of marginals. This is fine, right? We have already shown the marginal property implies that I'm not changing the ones that I'm actually have data associated with. So I'm now going to say that I got a set of f's, which corresponds to y's, and I'm also having a set of u's, which doesn't correspond to anything, and I also, the inputs to these u's are z's. So I'm basically taking another set of marginals. Now what I can do now is that joint distribution, I can just use the product rules of probabilities and write this as this, where I now say from right to left, I say I first look at a set of input locations z's, then they correspond to some output y's, some specific marginals, and then I'd say now I look at the f's, which corresponds to these x's, where I know the information about the u marginals. Okay? So it's effectively a set of function values that I've hallucinated. But I'm not changing the GP at all, because remember, the GP is infinite. So my projection now changes, because I now decide to pick down a set of additional marginals. So now then comes the trick which Michalis thought of in 2008. So he said this. Let's hope this math is correct. He said this. Well, instead of thinking of u and z as just additional random variables, I'm going to think of these as variational parameters. And the variational parameters are the ones we called theta before. They were the ones that parameterized q so that I no longer needed y. Okay? So the idea is then, can I pick u and z such that u and z contains all the statistics of the posterior, so that I no longer need the data. Hopefully this will make sense when we derive this. So it's a very, very clever thought. So now we've introduced another set of variables. So if we want to do a variational approximation, we're going to approximate all these. So we have q of u, which is supposed to approximate the posterior p of u given everything else. Q of f, which is supposed to approximate p of f given everything else. And q of x, which is supposed to approximate the posterior distribution over x. Okay? So now, what we're going to do is that we're going to try and derive this bound now, but now we're going to add this assumption that says that I want to pick the u's and the z's in such a way that in order to determine the posterior distribution over the approximate posterior, they contain all the information, so I no longer need the data. There's an error in this slide. This y here is a u. This one there is a u. Okay, so what we do is that I now take and write down this distribution here. And remember, P of x, we already picked P of x out when we went from L to L tilde. So I now write, I have all the approximate distributions here. I have the joint distribution up here. Now I factor the joint distribution in the likelihood, then the conditional GP prior, and then I have the GP prior here. So I pick Z, generate U, and then conditionally I generate F. Now comes the trick, and this is super cute, I think. Now let's assume that U, the U's that we're looking for, are supposed to be sufficient statistics for F. What that means that Q of F, as you saw here, Q of F is the posterior over F, which implies that it needs U, X, Z, and Y. But if U is sufficient statistics, so U contains all the information about F, then I don't no longer need Y, right? This is the whole cutting of that slice. And remember, I'm free to choose U. U are my variational parameters. So that means that Q of F is equal to P of F given U X Z. No dependency on Y. So what happens if we plug this in? So if we plug this in, so this is just a copy of the previous slide. If I plug this in, so I replace Q of F with P of F given U, X, Z. Well, now you get this. You now have the conditional distribution here, and which is the same as the approximate posterior. So now these two terms cancel each other.
Can we just pause a second?
Yeah.
There's a couple of questions where people are starting to get lost about what all the different letters mean, to be honest. So if you could just go through quickly and just remind us what like X, U, Z, and F are.
Yeah.
Basically, just because that's where everyone's going.
Basically, let's do whiteboard. So
yeah.
Let me see. What's the easiest way? Let me do this. I'll go to a function. Yeah, actually, let's do this. Let's pick one. No, actually, let's pick. Yeah, let's pick. Let's just pick. No, actually, let's pick this one, right? So let's say that I have observed. I know a value. And so let's think about regression now first, right? Let's just think about, you can do the same thing for regression. It is much easier, the harder the thing that we do. Let's say that I have a Y value, right? Which is actually, I'm gonna associate to X equal 3. So the red slice here. Yeah. So I got an X and a Y value corresponding there. I can move this around, right?
Sure.
Now, what I'm going to try and do is that what we defined the Gaussian processes is that we said that I can take another slice, any other slice, without actually altering this one. That was the definition of the Gaussian process.
Yeah.
So what I'm now going to do is that I'm going to pick the green slice. Yeah. The green slice doesn't correspond to an output value. I have no output value for it.
Okay.
Now I'm going to use that as a parameter that allows me to freely move the green slice so that I can parameterize the distribution over the red slice without knowing what the value is at the red slice. Now you can think about, this is trivial if I got 2 points, right? Because how would you parameterize the red slice if you had 1 green slice for it? You would put the green slice over
on
the red slice.
Yeah.
Job done, right?
Yeah.
But what we are going to do, and this is why it's called a sparse approximation. Let's now think I got 100 red slices, and I got 5 green slices. Your question is, how can I move the green slices around and put them in such a good positions so that the predictive distribution, when I take the green slices and do the prediction like this, such that the distribution over the red slices become exactly what they should have been if I actually knew those values.
Yeah.
And that's the bound.
Yeah.
I should actually make that as a slide, thinking about it. Does that make sense?
Yeah, I think that's good. I think the problem people are having also is just getting lost with all the actual, just remembering what all the letters were. So X's are like the observed like inputs, right? Y's are the, I'll make a note into the chat. Y's are like the observed outputs, right?
Y is the observed output.
Yep. Let me think, what letters were there that we need to define?
Yeah, it's a little bit of a tricky one.
There's just so many letters. I think people got lost.
Yeah,
so F is like the latent function at each of the observed outputs, right?
Yeah.
Each of the observed, and then there's just Z and U to worry about observed outputs, and then so Z is like the locations of those.
So Z corresponds to X. Z is in the same space as X. The reason why this notation is horrible, the reason why this notation is used is that this is how it's used everywhere.
Yeah.
I don't know who to blame for it, but this is the notation that you'll find in all the literature and in most of the code as well.
Yeah. What would you call them again? Because one of the questions I saw was auxiliary variables, and are they the same?
Auxiliary variables. Sometimes people call them inducing points and inducing locations.
And then finally, U are the values of the...
so U corresponds to F. So U are the additional marginals of the Gaussian process. And the cool thing about doing this is basically, you're effectively going through the definition of a stochastic process, which I think is a very, very cool thing. And it's a super neat trick. It's one of these things when you actually see it, and if you spend some time going through this math, it's one of these things when I actually understood it, I thought, blimey, that everyone should have come up with this, which is the real great science when things are actually obvious when you see them.
Cool. Well, I think people have got the hang of it now. Okay, so
cool.
Yeah, feel free to
so let's try, and I'm going to be a bit more. This was the thing that I wanted to go through in quite detail, and now we're going to jump at some. But basically, what this leads to is now. A funny one is that now you have an expectation over this P here. This P here is just a predictive Gaussian. So this is basically saying, if I know the Gaussian process at certain, I know what the values is at a certain Z location Z, those values are U. Now I want to predict what do I think the values are at a certain location X, and I get the distribution over those. And I take the expectation over, this should clearly be a log in here, the log of P of Y given F, which is just the likelihood. So another way of looking at it, you've effectively disconnected X and Y. X and Y no longer communicate directly. They communicate through U. And that's why we could get this integral solved. And then it adds an additional KL divergence down here. So the cool thing about this now is that this expectation, there's many ways of actually optimizing this bound, so we want to maximize it. You can, for certain covariance function, compute this expectation in closed form. You can also do sampling, you can do all sorts of funny things with it. And then you have these two KL terms. Now, the interesting thing is we talked about how can you place, we motivated this by saying that we need to place structure over X. Now, P of X only appears in this KL term, which means that it's probably quite easy to actually add lots of cool things over X, lots of different structures that you potentially want to have, because it only appears in this KL term. There's an additional thing which might be interesting for you if you're interested in running GPs on lots of data. This parameterization also allows for stochastic inference, so you can batch process this thing as well. So now I'm going to talk, oopsie daisy, I'm running out of time, but I'm going to talk about just IDs of priors that you can place. So the first thing we said is, I just want to limit the scale of X. Well, you can just put the Gaussian blob around it. Another thing which the Gaussian blob allows you to do is that if you specify a blob, you start off with an X, which is a 100-dimensional. Now, the prior is that I want distances on X to be as small as possible. The best X here would be an X where everything is in 0, right? So now I can actually learn the dimensionality of the latent space by just putting a Gaussian blob. And the way I do this is that you can add this in GPy, which I think you will use, where you can add what's called an ARD kernel. And what this allows you to do is to scale each input dimension independently, which means that the Gaussian blob is going to be tighter the fewer dimensions that it has, right? So now you can basically turn off dimensions. Another thing which people have done a lot is to place dynamic priors. So you can say, I have some temporal structure in my data, and now I want each X to follow some form of temporal structure. So now you can place a prior over that, and you can learn, for example, motion capture data. So I am gonna in the benefit of time, I'm gonna skip some slides because I wanted to talk about something that will relate to what Neil is talking about later. So hopefully what I discussed was reasonably clear, and that was quite detailed. Now I wanted to talk about something a bit more philosophical, because there's one thing that this bound leads to, and that is, now we have this flexibility of specifying priors over X. They can be whatever I want, because it came up so simply in just this additional KL term. So why not take something as crazy as putting a GP as a prior over the latent space? And why not put a GP prior on the input to that GP ad infinitum? Because we said that my motivation was that GPs are these awesome things, right? They don't exclude anything, but you can really concentrate their mass. So it seems like the best prior you can ever use. So why shouldn't I just put GPs everywhere? And this leads to then a composite GP. So let's say that I have this Y that I now observed, which is generated by a GP whose input comes from another GP, and so forth. And then I learn these x's. Or I can just extend this and have as many x's as I want. And I dislike the word deep because mathematicians call these composite functions, and I don't understand why we can't call them composite functions either. But another way of calling this would be a deep GP. So the first thing then to ask is that why do I want a composite function? Why do I want a deep GP in the first place? If you would ask a mathematician and you say, I want to learn a function and I want to learn it a composite function, a mathematician will just reply to you and say, well, a composite function is a function. Why would you ever divide up a function in lots of separate functions? It's still just a function. Why not just learn parameterize one function? It just seems nonsensical, completely nonsensical. Well, to me, there's one motivation for ever using a composite function, and that is if my knowledge is composite. So my generative process that have generated the data is somehow composite, because everything is defined or is about how can I specify strong prior assumptions over my functions. And if my knowledge is composite, then I should also have a model that allows me to input my knowledge in the right place. But this is not often how these things are described. So I'm going to have a little bit of a rant now on these things. So often people say, well, the reason why we do composite things is because these models are more flexible. And now I said that flexibility is not something that we want. It's a bad thing, because flexibility implies that you can learn anything. You're basically falling into the trap of the no free lunch. So for example, here is a function. If you would try to learn this function with a squared exponential kernel, it wouldn't work particularly well, because the length scale of this function is changing. But what you could do is you could take two exponential kernels and do a deep GP, and you can learn this. And it will fit it really well. Because what the first function will do, it will stretch this thing so that it will look like a sine wave, and the second one will perfectly fit it. Well, now this is a bit tricky. Now you've increased the space of possible solutions, and you can now fit anything that you want. And I'm going to try and highlight this. Then I got an additional annoyance. Often you see that people motivate these things because supposedly there's hierarchies of information. And I'm sure some of you have seen these kind of slides where you say an image can be decomposed. If I take a face, first I have faces, and a face is composed by eyes and noses, and each of these layers will decompose into these different hierarchies of complexity. This doesn't make any sense at all to me, because when I describe this and how it's described as an additive structure. A face is composed of two eyes plus one nose and a mouth. I added these things. A composite function would be more saying, I push an eye through a nose and now I get something else. It doesn't work like this. So why would you then want composite functions? So let's just think about the characteristics of a composite function. So the first thing a composite function does, I just need to check, how are we on time?
Yeah, we've got 5 minutes to the end, but we can run over like 5 minutes, I guess, 10 minutes.
Is it okay to run over 5?
Yeah, I think yeah, that'd be fine. Yeah.
Cool. So basically, the first thing that I think about in terms of composite functions is that, so what are the characteristics that I get? Well, there's two things. It's the kernel and the image of a function. So the kernel is all points that map to the same value, and the image is the possible set of output values that the function has. And, raise the hand.
Uh-oh.
Now my slide disappeared.
Yeah. Cool, it's back. We can see it.
Should I keep going?
Yeah, sure. Go ahead. Yeah. Was there a problem?
So one of the things why you want to build what happens when you do a composition is that basically you can think about it on the leftmost image. So as soon as I have a function which is non-monotonic, I'm basically tying points of the input space to each other. So if I push the output space of this function, is basically going to make that point and this point indifferentiable. Because in the next input to the next function, they would have the same value, which means I've effectively folded the function or the input space on top of each other. I'm basically collapsing the space. And an analogy of that is, let's say this. Let's just take distributions because that's what we're interested in. Let's say I take the real line between 0 and 1, and I place a uniform distribution over this. This is all possible mass. Then I push this through this red function. Push this through this red function. Now I'm going to get these 5 blobs. Okay? So now I'm going to say that, just for the sake of an application, is that I'm going to say that 2 of these are cats and 3 of these are dogs. Now I'm going to push these through another function that looks like this, dunk, dunk. If I push this through, I've now folded all the cats on top of each other and all the dogs on top of each other, and I've ended up with actually something that looks like this. I've taken the whole real line and collapsed it into 2 points. This is great. This is awesome if everything that you want to do is classify things. If you want to collapse an input space into very, very few things. Now the problem, there's 2 problems with this, is that a tiny variation in here, a tiny variation in the input is going to make you jump between one of these points on the output. There's nothing in between. You're always 100% in one of these locations. So now, this is cool. This is one of the reasons why neural networks have worked so well, is that it has this collapsing effect. So now one of the things we like to sit on our high horses, and we like to think that, great, everything they can do, we can do better because we have some actual rigor and principle. So why shouldn't we just take these models that they have, composite functions, which are just motivated why they can be useful, and just put GPs on them? That's awesome, right? We are therefore going to do much, much better because now we've got probabilities and everything. So now, one of the things, let me see, I'm rushing a little bit on time here. One of the things that, let me see, I'm just going to rush this. Yeah. So one of the things that actually happens in this case is that it's not as trivial to do as just saying, I'm now going to replace all the functions with GPs and I'm automatically going to do much better. Because one of the things that we need to think about when we're doing GPs is this. So how many of you, when you saw, well, I can't ask a question, but when you saw these types of plots, how did we actually interpret these plots? The first time I saw them, I interpreted that, well, great, there's a possibility that a value at -8, I believe the value at -8 is somewhere in between here, between the blue lines. That's how I interpret this. This is very strange because that's not at all what this actually says in terms of functions. Because what a GP is, a GP has correlated everything along the input axis. So you can't look at the marginals. Plotting these marginals, I think, is not a very good idea. And what happens when you do this compositely? This is when very strange things happen. So let's plot some marginals. Let's say I now take a flat function through a sine function. So I push the uncertainty from the red one through the green one, and I end up with a blue one. Now, if I go in and pick any point in the blue region, the location of any of these points, the uncertainty, could either be contributed, because what this red line does is that it basically takes the uncertainty in that one, takes the sine wave in the second layer and moves it back and forth, while the green one is basically moving it up and down. So that means the uncertainty at this point can come from any location. So now, if I would want to do a composite probabilistic model, I need to correlate the uncertainty in the input with the with all the inputs to the output. In the same way as when we looked at this graph, if I look at the point here, when I look at a function, I need to look at all points jointly. These plots, I think we should just stop doing and show samples instead, because samples correlate every slice, which is exactly what we've learned. If I do it compositely, I need to correlate all slices and all layers. So I'm going to finish. I didn't have time to do this properly, but I'm just going to show.
Feel free to go a little bit slower. We've probably got like, we can, you know, there's no real rush if you want to.
Yeah, no, I've already rushed it, so I think I've already ruined it. But what my point is, what my basic point is this. Let's just take this as an example. I have the square at the bottom right, and I want to transform the square at the bottom right to the square at the top left through a set of rotations and translations. Now, there's no uncertainty of where I want to end up. But if I composite this transformation as a rotation, translation, rotation, I can pick lots of different rotations. Dependent on the rotation I pick a translation and the rotation and the translation. If you look at these as marginals in each step, you would say it's possible to do these rotations, it's possible to do these translations, it's possible to do these rotations. You will end up with tons of possible endpoints, because each one of these needs to be correlated. Another simple example is this. If I want to model this sine function as a composition, I need to pick, if I pick orange here, I need to pick orange here to get that function, and orange there. That's basically correlating the uncertainty across these things. And this is incredibly hard to do computationally, and it's also incredibly hard to interpret. So you'll hopefully see more of that from Neil. So I'm just going to finish up. Sorry for running out of time and messing up the last bit.
No, it's great. Yeah, thanks.
So the things that I talked about, just unsupervised learning. Often people see unsupervised learning as something hard and something that's more challenging than supervised learning. I don't even think there's such a thing as unsupervised learning. If someone tells you to do some unsupervised learning on data, if that implies that they have no requirements on the results that you get, well, it's super easy, right? They give you some data, hand them back the data and say, well, you didn't tell me what to do, so therefore here's the data back and I have my money, right? So actually, I don't think there's a thing as unsupervised learning. What it actually does is that it's more ill-defined, which means that we need even stronger priors to get out what we want. So therefore, we need ways of specifying relevant assumptions to learn something useful. GPs are really, really good at this, because GPs allows us to specify very, very strong assumptions. So basically incredibly narrow distributions over the space of functions, and they're also interpretable. So now, in terms of this thing that I didn't really have the time to talk too much about, is that it's very easy to just think that, great, now I have a bound which allows me to do composite GPs. I should just throw GPs on GPs. But don't do that, please, because you're basically throwing your prior out the window. You now basically said that you can model anything independently of what the prior actually says. So now, doing so, now you're stuck, because effectively no free lunch tells you that you cannot, you haven't constrained your sum or your hypothesis space sufficiently. So the thing we need to do, if we should, because there are examples when we need to do these composite functions, and that is, for example, reinforcement learning, where you have a natural composite structure. But if you want to learn in those domains, we need to think about how we apply these models, because it's not at all as natural when we add uncertainties and probabilities to these models. The narrative that we had in models that don't have it doesn't really fit. And with that, hopefully we can, at least that will lead to a discussion during the roundtable. I have lots more to say, but yeah, not time enough.
No, that's fine. Yeah, great. Well, we'll be able to like expand on a lot of this in the roundtable after lunch. So not
very good.
So it's fine. Hey, great. Thanks for that. It's been really useful for me anyway. If everyone wants to ask questions on the between now and then as well, if you want to ask on the Hoover app, that'll be a good way of doing it, or during the roundtable itself, that'll be great. Cool. Thanks again, Carl, for that. That's really good. Ritzio, I think it's what's the plan now? I guess it's a break for an hour or so, and then roundtable. Is that the...
Yeah. So thank you, Carl, again. And yeah, so the idea is to come back at 2:15 for the lab session, and then at 2 for the roundtables.
Cool. Hopefully Carl can hear the virtual clapping for everyone. Sort of imagine it anyway. I'm sure.
Yeah.